The future of naval combat, as per any domain, is increasingly reliant upon visibility and awareness to the electromagnetic spectrum. This is increasingly important, especially in contested environments where we require operations against peer or near-peer adversaries. Concepts such as spectral maneuverability or adaptive communications is reliant upon awareness to the electromagnetic spectrum, and that's exactly what Spectrum SA seeks to provide. That insight, as well as actionable information to decision makers or to other systems and platforms present within the fleet. Spectrum SA seeks to provide information in multiple different areas. The first is the time frequency domain, where it seeks to provide information on what frequency bands are being used, by who and when. The second is the geospatial domain. Where are emissions occurring? Is that where you expect emissions to occur, or could that potentially cause some problem that could be mitigated by spectral maneuverability? Visibility to signals, their classification, and their location is also key, especially if those signals are unexpected or indicative of adversarial behavior. They allow for the formulation of a plan and an appropriate mitigation response to what's occurring in the environment. Lastly, Spectrum SA can be provided in real time, providing information on what's occurring in the electromagnetic spectrum at the moment, or historically, which allows for or enables the analysis of adversarial patterns of behavior. One solution to Spectrum SA at sea is the deployment of a broad number of low-swap, low-cost ruggedized RF sensors on an inexpensive fleet of unmanned vessels, whether they be surface vessels or aerial vehicles. This sensor proliferation builds in a resiliency such that if any individual sensor should go down or become damaged, the system as a whole retains its functionality. Further, it allows for the detection and localization of adversarial activity through a number of different proven techniques. Lastly, it provides the information required for adaptive communication networks and for adaptive or automated mitigation responses to any threats which are detected. The product that we've developed at Peraton for Spectrum SA is called SecureSense. SecureSense was specifically designed as an affordable and adaptive Spectrum SA solution comprised of a number of ruggedized, low-swap, low-cost RF sensors. For that, we've also built a scalable architecture that allows for hundreds or thousands of these sensors to be deployed simultaneously, and for their activities to all be coordinated from a central location, or for the sensors to operate autonomously. Each sensor performs a fair bit of edge node computation for signal detection, classification, and geolocation. And the system as a whole is capable of automated alerts, as well as sensor cross-queuing or triggering of other responses from connected platforms or connected systems. We also have multiple powering and data backhaul options, which allow for flexible deployment opportunities for the sensor. There are a number of SecureSense system features that support the concept of Spectrum SA at sea, such as those shown on this slide. But what these all build towards is a broad number of use cases that are made possible by having a flexible and adaptive system. SecureSense supports a broad number of different use cases, such as the ones that are shown on this slide. The first is distributed sensor networks. Because SecureSense sensors themselves are ruggedized and low cost, they can be affordably deployed in quantity on both static and mobile platforms, such as unmanned surface vessels. Having a resilient sensor network with minimal data backhaul requirements is key to operating in a contested environment. And one way that we've tried to achieve that is by having as much processing occur on the sensor node itself as possible. The second use case is comprehensive spectrum situational awareness. Individual sensors are only going to be able to say so much about what's occurring in the environment, but by stitching together data from multiple sensors that are all positioned in the area of interest, you can provide a more comprehensive view to what's occurring in the electromagnetic operating environment. We do this both with composite spectrograms that provide global visibility in the time frequency domain, as well as mapping out where the spectral emissions are occurring geospatially to help for localization of those emissions or a greater awareness to where there might be contestation or just congested electromagnetic frequency bands. Signal detection, classification, and geolocation occurs at the edge node. Again, that helps to minimize our data backhaul requirements. But we also allow for multi-sensor operations, such as time domain of arrival or TDOA, which provides precise geolocation down to about 10 to 20 meters accuracy. This information can then be fed to other platforms to provide a mitigation response to deal with any unexpected or adversarial threats that might exist in the area. Spectrum visualization in the EMOE has to be intuitive, otherwise it's not going to be easily understood by decision makers. And one thing that we've done with SecureSense is build our spectrum data products in a way that an operator can very easily understand where emissions are occurring and whether or not those emissions are expected or anomalous. In April 2021, we participated in the Navy's IBP-21 exercise in San Diego, where a SecureSense sensor was deployed on a prototype long-range unmanned surface vessel system. You can see concept art for it on this slide. Our sensor was mounted and operated continuously for 72 hours at sea without difficulty, and where it was able to perform continuous spectrum monitoring with no a priori knowledge of what signals to look for. We were able to do signal detection and able to identify patterns of persistent signals, as well as for those which were more intermittent or anomalous during the time period of testing. The map in the upper right shows a sensor position and also shows how with even an individual sensor, one can map out where signal strength is relative to where sensor position is. All the measurements made during this exercise were geo-stamped as well as time-stamped, which allows for historical spectrum assay to come in and perform a wide range of different analyses. We're currently conducting additional analysis of results in coordination with our Navy stakeholders and are looking to the next experiment to expand upon this first round of more limited testing. Test results to date, though, do prove and demonstrate the concept of a low-cost sensor on an inexpensive unmanned platform that being able to provide spectrum assay information back to the fleet. We were able to connect the sensor via a satellite link during the operation, and were able to record all the information in a way that also allowed for post-processing analysis. To summarize, spectrum assay is critical to advanced and autonomous naval operations, as well as for any adaptive behavior which is required in contested or congested environments. Distributed RF sensing, such as what we make possible with the SecureSense technology, allows for a resilient spectrum visibility, which can inform a dynamic communication system, networks, or weapon platform behavior that require triggers to only operate on targets of opportunity or signals of opportunity as they are detected. SecureSense has been demonstrated through the IBP-21 exercise. We were able to operate continuously. We were able to provide information which was both informative and actionable, both during the exercise as well as after the fact to Navy decision makers. And it really proves the concept of what you can do with a low-cost sensor in the naval environment. There are multiple future directions that we're looking to explore at this time. The first is to expand on the individual sensor exercise into a multi-sensor exercise, where we would look to coordinate sensor scanning profiles, as well as to synchronize signal detection and sensor cross-queuing activities, such that sensors can always be looking in the bands of interest for signals that are more actionable to other fleet operations. Expanding communications out such that the spectrum data products from SecureSense go to other naval platforms would also benefit an overall naval exercise that we're looking to move to as next steps. Signal classification and localization results will inform overall naval situational awareness, which will overall benefit the warfighter and the fleet. And then triggered actions using the sense spectrum data from SecureSense or similar platforms to queue responses by other systems and platforms for either spectral maneuverability, dynamic communications, or for a targeted mitigation response. Thank you very much for listening to this presentation. For additional information, please feel free to contact me using the information here, or feel free to swing by our website and look for additional information on the SecureSense technology.